Okay, so good morning, everybody. Today I'm going to talk about distance geometry in linearization norms. And this is a joint work with Leo Liberti, who's the expert in distance geometry problem. I started working on this topic a few years ago, so I'm not an expert at all. But in this application of distance geometry, we used mathematical programming tools, and that's what I will talk you about. Okay, so Antonio already nicely introduced the problem, but I will just give you an idea of, just briefly reintroduce the problem to introduce the notation that is almost the same as Antonio's notation, but with a small difference. So in DGP, we're given an integer capital K that is positive integer that represent the dimension in which we work. And then we're given a graph that is, as in Antonio's talk, composed of a set of vertices, a set of edges, and then we use D for the weight on the edges instead of delta. And what we want to find is a realization function x that satisfies this constraint here. So this set of constraints, so one per each edge. So actually what we are going to consider, instead of the classical Euclidean distance for the distance between the vertices, is to consider L1 or L infinity norm. So so we have some applications, but I won't talk about those. These two norms are interesting because there are some applications, but also because these are easily linearizable. So I will show you some mathematical programming tools, some mathematical programming models that can be used to solve this kind of problem. In particular, in order to do this, the first step I need to do is to transform this nonlinear feasibility problem to an optimization problem in order to use mathematical programming tools. In particular, I will transform the problem into a minimization problem in which we want to minimize the difference between the distance, between x1, xi, and xj in the norm that we pick, minus dij. So basically, you want to minimize the infeasibility of the constraints I showed you before. And of course, there is like a mapping between the feasibility problem and the nonlinear optimization problem, because when we solve to global optimality the problem 2, and we find a solution, a global optimum that has value 0, objective function equal to 0, then it means that the realization for DGP exists. If the objective function of the global optimum is greater than 0, then it means that the realization doesn't exist. Okay? Okay, so now let's focus on the case of L1 norm. So in the case of L1 norm, we have the minimization of the sum of over the set of edges of the absolute value of the sum over k of the difference between the distance in L1 norm of xi and xj minus dij. Okay, so the first step, so we might try to solve this problem, but it has been done before, but actually we know that in the case of L1 norm, we have an advantage. So we can easily reformulate this problem in such a way that we use just linear functions. And we know that typically the solvers for linear programming with also integer variables are way more efficient than those for global optimization problems. So that's why we make some reformulations that bring us to an equivalent problem, but with more variables and just linear functions. So in particular, the first step in order to reformulate this problem, so to linearize this problem, is to introduce variables that are continuous, and there are Sij for each edge. So we can bound them between 0 and Dij, and they basically represent the outer absolute value here. Okay, so we can, at this point, minimize the sum of Sij over the edge set, and then just rewrite this problem in this way. So put Sij in the left-hand side and right-hand side of this, and then we will get exactly the same problem from here to here. Okay, so this can be done with just this constraint because we are minimizing. So it's given that the global optimization will be a Sij that will end up having either a tight inequality here or the other. But here, as you can see, we have linearized the outer absolute value, but we want also to linearize this in order to have just a linear functions to deal with. But this has to be done in a slightly more complicated way because the absolute value is not anymore in the objective function. And we do it by introducing variables t plus and t minus for each ijk, for each index ijk. That so basically I plus ijk plus t plus ijk plus t minus ijk represent the absolute value of xik minus xjk, basically. And then what happens is that we can write this like this, and plus we need some binary variables that model two cases. The case in which the binary variable xijk is equal to 0 means implies that t plus is equal to 0, but t minus can be between 0 and dij. So this models the fact that xik minus xjk is non-negative, non-positive. Then we have the other case in which zijk is equal to 1, and in this case t plus, thanks to this constraint, can be between 0 and dij, but t minus has to be equal to 0 because we have bounds plus we have this constraint here. So it models the case in which xik minus xjk is greater or equal than 0. So basically, in this way, by introducing S and T, so continuous variables, and Z binary variables, we completely linearized our optimization problem. And what we have now is a mixed integer linear programming problem that we can solve with standard MILP solvers. Okay, so and this is the final, the reformulation that we will use. On the other side, so for the case of L infinity norm, so it's slightly different. So the first step is exactly the same, meaning that the outer absolute value can be as well linearized as we did before by introducing a variable s that are continuous. But then, as you can see here, we have a max, so we have to deal with it in a slightly different way. So this is the model coming from the first step. So basically, in the second step, what we do is to take this and linearize, so get rid of the max by just adding a constraint. So basically, having a constraint of this type for each k. Because of course, if it has to be valid for the maximum of this over k, then it just means that we can impose this constraint for all k. And then the second part as the index and as the sense of the inequality is not the same, then we have to do a slightly more complicated linearization, and in particular we want this to be this constraint to be satisfied just for the maximum. So we need to introduce again some binary variables and to impose these constraints only for one wik greater or equal to 1. So basically just one of these wijk will be equal to 1, and it will impose this constraint here. So from here to here we got rid of the max, and we added the binary variables. And the last step again is exactly the same as we did before, in which we just needed to model, to linearize the inner absolute value present here, and we do it by introducing again t plus, t minus, and zijk. So, and these are the two reformulation that we propose for this case. Okay, so the first thing that we did was to test these formulations and to give them to Cplex, that is a commercial solver that solve like large-scale typical mixed integer linear programming problems. And we generated some instances, in particular 35 instances for each of the two classes of problems. So a set of nodes goes from 10 to 40, and then we made sure that there was a feasible solution for each of the instances. So do you have a few minutes? Okay. So then we set a time limit of 10 minutes, and then so we have to. I mean, actually what happens is that not all the time we were able to find feasible solutions, and in particular, so feasible solution for the, meaning for the DGP, but we measured the error of such a solution thanks to I would say standard measures, in particular the mean distance error and the largest distance error. And I will show you some computational results using these two error measures. Okay, so first table concerns both MILP1 and MILP infinity, so both models. For each value of n, that is the number of edges, and each values of s that I didn't explain, but it's just a measure of the density of the graph that we generated. We reported for each of the two models the two error measures of the solution we found and the CPU time needed to find it. And in particular, you can see that if we focus on the L1 norm model, actually the errors are like, I would say, not so high, and the CPU time also are reasonable. Up to 25 here. For the L infinity norm case, actually already for 25 with the dense graphs, it starts being complicated to find the optimal solution of the MILP problem. Meaning that here we hit the time limit, and then we have an error that is not negligible, I would say. If we increase even further the dimension of the graphs and go up to 40, again with the same like variability of density, the L1 norm model scales pretty well, I would say, while this is not the case for the L infinity norm. That appears to be more difficult, and this is clearly because it's more complicated, also because it has more binary variables, etc. So here you can see that in the dense, most dense instances, we always hit the time limit, and the error is not negligible. So I do not have time to speak about the other things that we did, so we proposed in the paper, you can have a look at it, some heuristic ideas to improve these results. But with this, I would like to thank you, and I'm ready to take questions. Yeah, you can. Yeah, actually, I didn't add the. So actually, I didn't add the constraint, but we add the constraint that where the sum of the x is equal to 0 in order to get rid of some symmetry problems. Yeah. Mm-hmm. Yeah, yeah. Actually, we constructed the graph in order to have always a solution, but it might be not the case in random general instances. Yeah. Um, I think. Let me think. Yeah, I think you can like do some post process in order to check what went wrong. I think, yeah, in some sense.
You are not, as in the first presentation, prioritizing distance, like local distance against, like short distance against long distance. You are not putting weighted.
No, yeah, no, 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 no.
So you sacrifice on everywhere.
Yeah, basically yes. In this case, yes.
Right, question?
Yeah, I have a question. Do you think that even for the Euclidean case, you could use this approach to as a process?
Yeah, actually yes, because yeah, I think so because of course, I mean there is a relationship between all the norms. So you can think the solution of the two models as an upper or a lower bound to the Euclidean case. Actually, yeah.